Okay, so let's talk and see what we remember about acids and bases. Some general properties of acids. They taste sour. Think of all your citrics, lemon juice, citric acid, Sour Pouch Kids, ascorbic acid. They can dissolve a lot of metals. Acids can neutralize bases. Acids are red. Acids are red, bases are blue. They changed the litmus paper to red. The reality is you don't, if you've noticed on the AP test, it's not a lot of just memorizing. So this is probably not something that is the absolute most important of this unit, just a few reminders. Here are some common acids. Hydrochloric was in your stomach, also used to neutralize the pools, or if you need to acidify your pool. And this is again just kind of for your informational purposes. What you do need to know. Acids, remember, need to have that hydrogen. So we can talk about a binary, and a lot of this is just some of the vocab today. Binary, of course, just means two elements. So if it's a binary, it has to have hydrogen and one other. Quite a few of our strong acids are binary acids. Probably one of your most common binary you're going to see is HF because it's a weak acid, and we're going to talk a lot more about strengths in just a minute. Okay, bases. Again, just some reminders. Bases, they taste bitter. Soaps, shampoo, if you've ever gotten those in your mouth. They are slippery. Again, soaps, shampoo. They will turn red litmus paper blue. We will be using indicators, and you've already had the experience with indicators, and we know that they just will change colors depending on the pH levels. We're not doing any pH calculations today. We will do that in class. And so if acids can neutralize bases neutralize acids. We've already talked about how acids and bases like each other and form water. So again, here's some just kind of informational purposes. A lot of the bases, you don't think about them. They're very, very caustic, which means they can also cause a lot of damage. Drain cleaner is a base. I have put some holes in my clothes with some strong bases too. So acids aren't the only thing that you need to worry about. Okay, so let's look at our definitions. Arrhenius is more the traditional. This is the traditional. And these tend to be your strong acids and bases. That you have the hydrogen has to be in it, and the base has to have the OH. So NaOH, lithium hydroxide. Okay, problem was that didn't cover all of the compounds that can act like a base, so they expanded the definition. And so Bronsted-Lowry will include everything that Arrhenius did, but they kind of broaden the definition, and so your definition is it's a hydrogen. Okay, another word for hydrogen is proton. So it's a proton donor or a proton acceptor. And what that is, ammonia, all of a sudden in water, they realized that, and this is what we're showing in water, that ammonia also acted as a base, and it accepted, so look at over here, it had 3 hydrogens, but now it has taken one more hydrogen in, so it accepted a proton, and it is acting as a base because look at what's being produced. It is producing OH when it accepts that. So most of your Bronsted-Lowrys, you have water involved because it's saying how does this react with water. And then a Lewis is an electron pair donor acceptor, but you know the nice thing, we don't have to worry about Lewis's. So if you ever find old test questions and they're talking about Lewis acids or bases, skip that question. That won't be on your test. Okay, this hydronium ion. Hydronium is just the official name of what this hydrogen will do in water. It's going to attach with the water. That's why you see the extra water, and it's positive. You need to recognize these are the same thing. They're the same thing. And even on the same test, I've seen it written different ways. the test is written by different people, and it's just really what that question writer, what way he prefers. I used to always do hydronium. I'll be honest, hydrogen's a little bit easier. It just kind of depends if water is involved in the equation or not. So whether or not you use hydrogen or hydronium, you still need to just kind of look and say, is the equation balanced? So if water is in part of that equation, you need to have hydronium. If water was left out, then you can just use the hydrogen. So here again, this is showing you with the water. That's why we used a hydronium. So another way you can see this, and I believe even on the formula chart, hydrogen plus, this is a very common, that is a Q, that's a very common generic. You should recognize HA is an acid. And what's telling me it's weak or strong will be my single arrow or a double arrow. But both of these equations are saying exactly the same thing. Okay, these words, the conjugate base and conjugate acid. You need to know these. This is what will show up again and again and again and again and again and again and again, because we're going to talk so much about weaks and what is being formed in that beaker. I'm going to be saying, picture what's in the beaker, what's in the beaker, what's in the beaker. Sometimes you have to draw pictures of what's in the beaker. So we really have to focus on what is being formed when that weak acid or base is in water. So the conjugate base then is the partner to a weak acid. So a conjugate base is formed when the acid loses the proton. So the conjugate acid then is the partner with the base, and it is what is formed when that base gains the proton. So let's kind of practice these then. Conjugate base, remember, is formed from the acid. What do acids do? Acids lose a proton. So just take all of these acids and take away an H plus, and what is left behind? So HCl, take away an H plus, what's left behind is the chloride. HNO3, take away, and what do you have? NO3. Okay, NH3, take one H plus away, you have an NH2 minus. We are going to see a lot of organic acids and bases in this unit because we focus so much on the weaks. Here's acetic acid from the acetate. Remember, if you ate something you felt icky, acetate ion. So take it away, you have your acetate. Then we have a methylamine. Look at this. Okay, now when you take away, never take away from the hydrogens around the carbon. You're always going to take one of the branch hydrogens away. Branch meaning one of the end hydrogens. Never ever remove the one. If we drew this, you would actually have these hydrogens are on the carbon, and then we had 3 hydrogens over here, and so it was one of these 3. It's on the nitrogen, and that's where we're gaining or losing. Never take the ones away from the carbon. Okay, now we wanted to write, I can't see the whole thing, sorry, this is on your notes, it says the conjugate acid. So if I'm writing the conjugate acid, that's when bases gain an H plus. So just take all of these and add an H plus to it. So fluoride would become hydrofluoric acid. Ammonia, now this is where we have to get used to these words. We're going to see this one so many times. This is ammonia, and ammonia forms the ammonium ion. So ammonium is the conjugate acid of the weak base ammonia. Water, you're going to add hydronium. So the hydronium is the conjugate acid of water. H2PO4, add, and you get phosphoric acid. We're going to keep practicing that. So this is why we just do it right after our equilibrium. So look at the equilibrium. It's still products over reactants. These will all be in concentrations. And again, the Ka, this is assuming going back from the reaction that we had a couple slides ago, and you had your acid, and it formed the conjugate base, and in this case we had hydronium. So this one is when water was included. This was the other generic one. They both mean exactly the same thing. And we never include water because water is a liquid. So that's why we can write the reactions without water, because water is not going to be in our Ka expression. So a strong acid then. A strong acid means you get pretty much 100% ionization. You get mostly all ions, so 100% ionization. Pretty close to 100% ionization. So that means if you are ever asked to answer, is this a strong or weak acid, you have to talk about the degree of ionization. How many ions are being produced? Because that is the definition. So since that's the definition, that's what you have to talk about. You can't just say, well, because it has a small Ka, it's a weak acid. It has a small Ka, which means it's not producing very many ions, therefore it is a weak acid. So weak acids are going to have the very small Kas. But again, why? You don't get very many products. What are your products? Ions. So therefore, you aren't producing very many ions. It is a weak acid. So looking at these pictures, just different ways, okay? So if they give you some diagrams, this is the acid. Okay, look at this. Pretty much there's no acid left. It's 100% ionizing. This would be a strong acid. Okay, but look at this one. Look at how many of the ions stay together. So these are your reactants. Here's your products. Very few products. Very small degree of ionization. So therefore, this would be a weak acid. Okay, on your note, I want you to do this. I'm going to talk about this in class. I want you to show me what it would look like. So very common thing for an acid is the little teeny tiny hydrogen. So use this as a picture of an acid. So this could be your fluoride, and this is your hydrogen. I'm not going to try to squish that in there. That's the hydrogen. Same thing. Oops, that's not a perfect. Okay. And your little teeny tiny, this could be the chloride, and chloride is a little bit bigger, and this is your hydrogen. Okay, so these are your acids. Draw what you would see in the beaker for each of these if HF is weak and HCl is strong. And I will start and look at our pictures next class. Okay, there is a relationship between the conjugates. The stronger the acid, the weaker its base. So they're opposites. So the weaker the conjugate, or the weaker the acid, the stronger the conjugate base. That's actually what we're going to care more about, especially when we start doing some salts. Okay, these, so it's your bottom. Whoa, you absolutely positively have to know these. You have to know these. You have to know these. You have to know these. Because when you're looking and saying, the very first thing you're going to have to do when you have to calculate the pH is say, is it strong or weak? So you have to know your strongs, and if it's not one of these 7 strongs, then it's weak. And because of that, we really, when we start looking at salts, because we're going to say, is this an acidic salt? Is it a basic salt? Is this a neutral salt? It all depends where the conjugate came from. And the conjugate, so the stronger the conjugate base will be coming from a weaker acid, but you have to know if the acid is strong or weak. So there will be a quiz coming up that has these on it that you just need to know, is it a strong or weak acid? So looking at these, so the Ka values are given, okay? We know that you're going to rank the stronger, again, the stronger the acid, the weaker the base. So out of these given, the strongest acid of these, look at their exponents. So the strongest acid would be HNO2. So therefore, this is going to have the weakest conjugate base. This is the weakest acid, So it is going to have the strongest conjugate base. So from these three, I know that this is going to be the weakest. HNO2 is going to be the weakest of these, and then you would have acetic, and then you would have your cyanide ion. Okay, but let's look down here. The conjugate bases. So we first know the chloride because this came from HCl, which is a very, very, very strong acid. This came from H3O+. That's why it was next. Then we ranked these are as the weakest. Again, we said the weakest, then the nitrite, then our acetate, and the strongest of the conjugate is going to be the cyanide because it's coming from the weakest base, or excuse me, weakest acid. So the stronger the acid, the weaker the conjugate. We actually are going to care more about the opposite of that. The weaker bases are producing stronger conjugate acids. So finishing up just with some vocab. Sulfuric is a diprotic. So remember, di, 2, protic is a proton, which is a hydrogen. So any acid that has 2 hydrogens is a diprotic. So what we'll realize, it actually will have 2 separate reactions. So it is a strong acid, but that's only losing 1 hydrogen at a time. The second hydrogen will come off much, much weaker. When we look at pHs, we'll kind of talk about that. Okay, another definition, oxyacids. Again, look at the word. Oxyacids have oxygen in them. Okay, this is what is important. Again, because sometimes you're asked, circle the hydrogen it's going to lose. You always lose the hydrogen that is attached to the single bonded oxygen. And when we go into drawing second semester, we will definitely spend some more time on this also, but it's always the hydrogen connected to the oxygen, that's the one that is going to be lost. So when you talk about the strengths of the acids, you're talking about the strengths of this bond. If it's a very strong bond, then it's going to be a weaker acid because this is not going to ionize very easy. If this is a weaker bond, then that means hydrogen ions will come off easier and it's going to be a stronger acid. Those are common types of questions to show you understand the concepts about the strengths of acids. Okay, so with that, look at what happens. As these two are my strong acids, and then we start getting weak. Look at the difference. It's the amount of oxygens. So as you add more oxygens, what you are doing, I have a picture here, so as you add more oxygens, these oxygens are taking away. So again, this is where the bond that we're talking about. Remember, this is the bond that you're talking about. So this bond must be pretty strong. So it's not very hard, or excuse me, it's harder to ionize that hydrogen. So therefore, it's not producing as many hydrogen ions. It's a weaker acid. So the more oxygens, remember, oxygen is very electronegative. It's stealing electrons. So it is stealing more of the electrons away. And so it's making this bond weaker as you add more oxygens. So as this bond is weaker, you are making a stronger acid because this weaker bond means it's easier to ionize. Therefore, you're going to produce more hydrogen ions. If I produce more hydrogen ions, I have a stronger acid. So this is my strongest. Look at, there's 3 oxygens stealing those electrons away, making this a pretty weak bond. If it's a weak bond, it's going to be easier to ionize. If it's easier to ionize, you make more hydrogen ions. Therefore, it is a stronger acid. The same thing happens with electronegativity. Remember, down a period, fluorine is the most electronegative. So the further you get from fluorine, the least electronegative. So chloride is more electronegative. Same thing, it's stealing more electrons. This is a weaker bond. It's going to be easier to ionize. So it's all about the strength of that hydrogen bond in that, not hydrogen bond as far as the intermolecular force, the hydrogen bond between the oxygen and how easy it is to ionize, produce more ions, stronger acids. Like I said, we're going to see a bunch of organics. Key thing, if you see a picture of an organic, we don't freak out, but if it said circle the hydrogen you're going to remove, never ever ever remove a hydrogen attached to a carbon. This is the hydrogen you're going to ionize. This is the hydrogen is going to ionize. I just didn't draw it, but that's what it means. It's not OH like the hydroxide, it's O connected, bonded to the hydrogen. Again, vocab, but look at it. Halic, this means it's a halogen. Now, if you noticed, all the halogens, not all, most of the halogens were strong acids, HCl, HI, HBr, so when you're memorizing them, know that 3 of the 4 halogens. HF is a weak acid. Now, sometimes you're like, well, wait, but it's very, very electronegative. What happens is this fluoride is so small that this is actually a very strong bond, and since that's a very strong bond, it's not going to ionize very easily, so therefore that's why it is a weak acid. So when it talks about, you can definitely absolutely say they give you a list of Kas, which is the weaker acid. Use the Ka as a starting place. HF has a smaller Ka, therefore it is a weaker acid. A smaller Ka means it's producing fewer hydrogen ions, making it a weaker acid. So just make sure that you talk about what a Ka means and don't base it just on the Ka. So last thing, an amphoteric. No, there's one more thing, sorry. Amphoteric is something that can act as an acid or a base. So water, when you have water, it can actually lose and form an H3O plus. Sometimes in air, sometimes water will form an OH. Depends what it's partnered with. So NH3 in water, and you're going to get your ammonium and OH. So this is your base, this is your acid, this is your conjugate acid, this is your conjugate base. But look at HSO4 in water. It's going to gain, nope, you know what sorry, because it can do both. It can do that. I guess I should have written that down, because it can do both things in water. So it can, let's just finish that out. I was trying to focus on water, but HSO4 in water can also donate and act as an acid. So in here you can see water and your hydrogen sulfate ion are doing both things. Sometimes they lose a proton, sometimes they gain. So here it's acting as a base, because look at what it did. It gained. Water is acting as the acid, because what did water do? It lost. But here it's acting as an acid, because look what it did. It lost a proton. And here water is acting as a base because it gained. So you're having to track that hydrogen. Okay, so that is the last thing I want to talk about. I do want you to work on the book problems. They're just, again, conceptual. You can use your notes, you can use the book, just getting some of this concept, so then we can start, we're going to talk about it, but then we can also have time to start doing some pH calculations and look at how they're going to be different than how you calculated pH in pre-AP. And I will see you in class next time.